Let's start. Previously, we were finished with this topic of mathematical types of complexity, and we saw constant complexity, logarithmic, linear, quadratic, factorial, exponential. And now we are going to see that what are the different cases for the time complexity. We already know that there is one category that is called best case complexity. There is another category that is called worst case complexity. And there is another category, third one, which is average case complexity. We are already using these terms, but okay, properly definition wise, example wise, we are going to see it again. So what is the definition for the best case complexity? So best case, we know that it is the case when an algorithm will take the minimum number of operations. And what would be the situation? What would be the scenario when it occurs? So normally it is related with the input of the algorithm. So this case, best case will occur when the input data of your algorithm allows it to complete its task in a best possible way, in an optimal way. Best possible here means with the minimum number of operations. So that this can be the situation, but this case is rarely used. Okay, we are not using this most of the time, but as a knowledge, you can understand what it means. For example, if linear search is the problem and you have to find some element X in it, and if that element is available at the first position in the array, then at the first comparison, that element will be detected and given as an output. That would be the best case. Okay, that would be the best case. And when you have the best case, and here we are getting this with the minimum number of operations for linear search, only one comparison, so order of one. That is what? Constant. Constant. So the best case here is constant, and we can represent constant with what? Order of one. But it doesn't mean that for all algorithm, best case would always be order of one and other cases. No, the minimum, for example, it can happen that for algorithm, log of n would be the best case, or maybe uh, uh, order of n would be the uh, you can say order of n square would be the worst case, and order of n would be the average case. It can happen. Then you can understand that log of n is the minimum. So then you are saying the best case for that algorithm is log of n. But here for the linear search, it is order of one, because then we can understand that in an array, the element should be at the first position, and then you will match, and in the first comparison, you will say that element is available there. So for linear search, this is the best case. Now, worst case, when your algorithm is performing maximum number of operations. And in this case, what would be the situation of your input? The inputs would be your bad inputs, which will force the algorithm to do the maximum number of comparisons. So we are using this case, worst case, most of the time. Okay, most of the time, especially for research analysis, or for anything. If you developed some algorithm and then you are analyzing complexity of it, then you are also presenting its worst case only, okay? You are not most of the time discussing best and average case. You are not discussing. When you are giving worst case, this is maximum, huh? Then the other thing would be less than that. That would be the upper bound, you can say. So what is significance of this case? So this worst case guarantees the upper bound complexity as a upper bound. What it means, this is the maximum. Complexity can be lower than that or equal to that. So then there is no need to calculate other things. Those would be less than that, huh? So it guarantees that this is the upper bound of this will provide you the upper bound of the algorithm, and upper bound means algorithm will use maximum these different kinds of resources, huh? But mostly we are talking in terms of time complexity. Example for linear search. So for linear search, what is the worst case for that? When the element is not available in that, in the array. Then you have to, if the element are 5, then you have to do 6 comparisons that X element is not there. Huh? So that would be, so scenario is for this linear search example, when element X is not there, then you have to do maximum comparisons. So that would be the example of it, which is you can read it from here. Average case complexity. So what is average case complexity? You have to calculate the computing time for all the inputs. Whatever the input of the algorithm is, you have to calculate the time for each input. Then you have to sum up the time of all those inputs, huh? What is taken by them. And whatever the answer, then you have to divide it with the total number of inputs. That's simple, huh? Time taken by inputs, you have to sum those all times, and then you have to divide it with the number of inputs. Number of inputs. This is one way. This is the definition. And what would be the situation or scenario? Uh, in these situations, on the input, on the typical inputs, we are saying, or you can say simply input, you are calculating the average number of operations, average number of steps in that algorithm, which is we already defined here. What is the significance of it? Significance is this average case complexity would be more close to your real answer or solution. Huh? Normally, for example, normally whatever the data is available, normally if you will apply linear search over it, you will get average computer. You will expect that, for example, if for linear search and the elements in the array is normally distributed, then we can expect that, and if the size of the linear search is 5, then we can expect that in 2 or 3 comparisons you will find that. Huh? This is our expectation. Huh? This is our expectation. So due to this, it provides us more realistic expectation of performance of an algorithm than the other methods, which are the best and the worst. So, but it is a little bit hard to calculate because you have to sum and then you have to divide. And here we are discussing linear search algorithm, that if we have a linear search, then we will discuss all case. Then first thing is we will assume, okay, that all the inputs are distributed uniformly. All the inputs are distributed uniformly. Normally, it means that if n is the n number of the inputs, then 1 over n. This is what uniformly means, okay? For example, if 10 is the number of inputs in an array, then each element has 1 over 10 probability. Ah, but I'm not talking about probability here, okay? I'm just saying that each element has equal chance of appearance. Huh? So inputs are uniformly distributed, and including the case when x is not there. So then if x is not there, then I can say 1 over n plus 1, huh? Yeah. N plus 1 is the extra comparison after n, huh? That the x is not there. So then what? We will compute the time for n plus 1 cases, compute the time, sum them up, and then we will divide it with what? Again, with n plus 1, because now that n plus 1, and then you will get your average case complexity for that. Now, proving correction. Topic is changing here. Proving correctness. Up to this, if I will show you the first slide, describe fundamental concepts of algorithm design and analysis, including what? Symptotic notations. We are finished with the symptotic notation. Big O, omega, theta, huh? So complexity measures time complexity, space complexity. We are finished with it, huh? And now correctness proves we are here now. Okay, we are here now. So proving correctness. So if you have a symptotic, you have knowledge of symptotic notation, then after designing the algorithm, you can calculate by using those asymptotic notation, you can calculate the time and space complexity for your algorithm. But there is another thing that you have to analyze about your algorithm. What is that thing? You have to prove the correctness of your algorithm, that your algorithm is correct. You have to prove that. So in this proving correctness, what is general meaning? That here we are going to prove that this algorithm will always give us desired output, desired solution. Huh? This algorithm will give us always desired means correct, huh? Which is that what we want, huh? That what we want, and that would something we want some correct answer. So that always return the desired output solution for all legal inputs of the algorithm, for all legal different types of data for the algorithm. How we can prove that the algorithm is correct? There are different approaches here, highlighted with bulleted items. Huh? These are the bulleted, 3 here and maybe 4 here. And here in this course, we will go with this 3 and we will not go with that because we already studied these things. Even this thing and that thing, these two, we already studied in discrete mathematics, in the course of discrete mathematics. But this is something different here. But still, I am saying that we will go with these 3. Yeah? We will see counterexample, induction, and loop variant. And through these 3 different methods, we will try to prove that the algorithm is correct or not. Huh? So prove by cases or enumeration, prove by chain of if and only if, prove by contradiction or contrapositive. These are available in discrete math, so we are going to ignore it, but we will go with these 3. Correctness. First is through counterexample, indirect proof. The other name is indirect proof. In this counterexample, we will search for some counterexample. If somebody is saying that my theory is correct, then according to that theory, you have to search some example, counterexample, which means that example which is making that theory false. Okay. And if you will provide that counterexample, then that theory would be negated. Huh? And until you don't find any counterexample, then it means that theory is still correct. Huh? Until you found a counterexample. Induction, which is a direct proof. This is the mathematical induction. I know that you already have the knowledge of mathematical induction through your discrete mathematics. we will use this method again to prove the correctness of the algorithm. But mainly we are using these induction proofs for recursive algorithm, but you can also use it for the loopy algorithm that involves loops, and algorithm that involves recursion. You can use it for both the cases. But for recursion, it goes very smoothly. Huh? And then loop invariant. So if you know this induction, then it is similar to that with a different concept. So this is also a third method through which we can prove that the algorithm is correct. But here, this loop invariant, we will use only for those algorithms which will have the loops. And I will start this after Adhan, inshallah. Okay. So as I said that we will go with these three options. So that's why we are going first with the counter example, the method which is showing uh, correctness of an algorithm by a counter example. And to understand that, we will take this problem, and that problem is interval scheduling. That problem is called interval scheduling. So what is this problem? In this problem, we have a resource and we are representing that resource with R. And this is what? This is classroom. We are representing classroom with R. Or class or classrooms. And a bunch of requests. And this we are representing request with Q, and that Q will contain the starting time and the finish time. Okay. You can assume that in our faculty, teachers has requested that I want that for my course, this would be the starting time and this would be the ending time. And like this, all the teachers are submitting these requests with the start and finish to Al Khudra, you can say. And then these requests, we are representing it with Q. And then there are classrooms available here, and Al Khudra has to allocate these classrooms to these different courses. And we are calling these classrooms R. The question is, how can we schedule these requests to use the resources by taking care of the following these two conditions? So now we have to schedule these resources, which are what? Which are classrooms according to the requests. We have to schedule it, and according to these two conditions. I have only made this slide a little bit short, okay? Nothing else, okay? If you will see this slide on the blackboard, I have reduced one comment from it, nothing else, okay? So number one, so the first thing that we should have to take care, identify a set S of request such that no requests overlap. So as an answer, we have to, and here if you will see, set S1 is equal to this one containing these requests. Set S2 is containing these requests with start and finish time. This is the starting time. This is the finish time. Okay. And S3 is also containing these and starting with start and finish time. And here we are representing that this is time, going like that from left to right in a horizontal way. So we have to identify a set S as a solution that will contain requests, and in that set, no requests will overlap. Will overlap, and you can understand what it means. Overlapping. If this request is going from this is the start and this is the end, no any other can start when the previous one was in process. Now number two. The S will contain the maximum number of requests, and we have to keep maximum number of requests. We have to entertain maximum number of requests in S. Oh, if we will think over it, then from this, okay, we can see that this S2 has 6, S2, S3 has 5. So from these sets, I'm not executing any algorithm. But from these three sets, S2 is something containing more number of requests as compared to other. But anyhow, now this is the question, this is the statement of the problem. We are now, now some, if we will build this algorithm to solve this problem of interval scheduling, if we will build this algorithm for that, then at the end we are asking a question that this algorithm is giving us an optimal solution or not, which means this is giving us desired output or not, which means if it is giving us desired output according to the condition, then okay, then we can say it is a, then this algorithm is correct, huh? Otherwise we will not say it correct. So now the name of this algorithm is simple greedy algorithm, and here the input would be what? Array A of requests. So we are assuming that we have an array A, and in that array we have request. We are representing those requests with Q, starting time, finish time, Q1, Q2, Q3, Q4, and so on. Huh? Such that how? For example, in the array, we will have something Q1 is request 1 with the starting time and the finish time. Q2 is the request 2 with the starting time, finish 2, and so on. Qn is the request with starting and finish time. Understood? And then output is what? Output would be some set S with tasks scheduled or talks scheduled. Talks mean lectures, huh? Or you can say task schedules or request schedules. Here the algorithm is starting properly. Here we are just giving what is the input of the algorithm, what is the output, and here we are starting it properly. We are passing array A into it. And then first sort talks by start time. So we have whatever our talks, which are Q1, Q2, Q3, these are our okay tasks, huh? Requests. So sort talk by start time. So this Q1, Q2, whatever it is given, sort them or reorder them by what? According to their starting time, S1. So Q1 would be, it means Q1 first. Less than or equal to S2. This is for the task 2. And less than or equal to S3 and so on, less than or equal to Sn. So we are considering only the starting time of the different requests or the talks, okay? We are considering only the different uh, uh, different request with the starting time. If now our logic or our philosophy is basing on this starting time, okay, and then initially we are taking that the S is empty, and then we have a loop for j is equal to 1 to n, so that will go from 1 to n. This is according to the size of the requests, huh? And then we are calculating that if Qj is compatible with S. S is what? S is a set which will have elements. Initially, it does not have any element in it. It does not have any request in it. Huh? So if now J is equal to 1, so then Q1, because J is 1. So Q1 is compatible with S. S initially has 0 request. Huh? Then you are taking Q1, and then you are checking Q1 is compatible. You have to see that according to the starting time, it is compatible. And then, okay, visually, how we are also running this algorithm visually. These are the different tasks, and then you can draw what? These lines, which is representing what? Starting time. Starting time of all the tasks. In this way, you can draw lines on each. It is already drawn in a gray color. Huh? Now, so Q1. So, okay, this is the starting. So now this is the Q1. It is, you will say it is starting from here, and this is less than from all others. Huh? It is starting early than all others. In other meanings, it is starting early than all others. So it is compatible. And there is no any request already existing in S. So that's why it is compatible. And then if it is compatible, we are putting that request into this S. S is equal to S union Q1, which means we are adding it to this set S. And compatibility means what? Current request does not conflict with any others. Anyhow, this is a comment, okay? Not needed and in the algorithm. So after this, you can see something. And then you will go back again, J is equal to 2, and then Q2 is compatible with S. Then you will say this is Q2. Compatible? No, because the previous is running. Not compatible. Then you will come here. This if is false, and then you will go again. You will check J is equal to 2, and then you are checking Q3. This one is compatible with Q1. No, because that previous one is running, huh? And then after Q3, Q4, Q4 is compatible? No, it is because it is not compatible because the previous one is still running. And this one, Q4 or 5, whatever it is. So 0, 1, 2, 3, 4, 5. It is also not compatible. This is also not compatible. This seems, I don't know, maybe at the exact point, huh? So that's why it is not compatible in this diagram because it is at the exact equality. But little bit difference is there. But anyhow, in the algorithm, in this diagram, it is ignoring it because it is coinciding with this orange one. Okay, it is it is intercepting the orange one, so that's why it is not considering. And this one, okay, this is okay. Now the starting time of this, it is greater than the previous one, huh? It is greater than the previous one. Starting time is greater than, and also starting after finishing the first one. So that's why it is compatible. That's why it is compatible. And if it is compatible, you are adding it into S. And in this way, you can go on for the next, for the seven, and this 8, 9, not. In short, these orange one is the solution. These highlighted in orange are the requests which will be considered if you will go like that. If you will go like that according to the starting time. And finally, when this loop will end, you are returning this S. Now the question is this algorithm optimal? Because what we have to do, identify the S. Okay, S is identified. And that S will contain the maximum number of requests. Already in these three sets, S1, S2, S3, S2 has the 6 number of requests, huh? Already in the and S1 has 4, S3 is 5. So maximum already we have what maximum we have 6. So the answer can be 6 or higher, huh? This is what I want to say. Anyhow, so is this a optimal solution? Because this algorithm is giving us solution S with 4 tasks which are highlighted in orange. So then this is not an optimal solution because 4 and this S2 is already given as an input with 6 tasks. So then this answer is not optimal. So then this algorithm is not correct. Okay. This is by on this algorithm. This is an example. Okay. This diagram that you have here, this is an example that you have run over this algorithm. And after running this example, you got the S, and then you are negating that this algorithm is not giving us the optimal answer. And we are doing this graphically in a picture, huh? In a picture. It is not, we are not writing anything here, but we are doing this in a picture here. Now, if we will modify our algorithm, if we will modify our algorithm according to the finish time, not the starting time. So this is if we will modify with the finish time, then it can be, then you will see that it will be optimal. I have given you the reason. By inspection, we see that we can choose different set of requests which do not overlap, but have more requests. This is, we are saying that this is not optimal. Huh? These lines are showing the previous algorithm is not optimal, because maybe if we have to think, uh, if if we have to think only with the start time, okay, okay, I will take this first one which is finishing here, then second here which is finishing here. Maybe for that, for this orange one, okay, I will take, then others are colliding. Yeah, for this orange, this is the only solution. But if I will take this one, I will I will ignore it. And if I will take this second one, this is ending here. Then I can take uh, maybe this one according to start time, ending here. Then after that, I can take this one and ending here. Then I can take this one, this one, this one. So I can take this as two, which is optimal. Huh? If 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 I will change the strategy, I will go with the starting time. But if I will change the strategy, I can get this answer, which is the optimal answer, not four. So I'm discussing that here, that due to these different reasons, this algorithm is not optimal, huh? Because we can get S with more number of requests. And then here, if we will go with the finish time rather than start time, finish time, again, draw these lines according to the finish time. And here the gray lines are drawn according to the finish time. Finish time, is it depend on the algorithm we design, or it depend on the operation that is going to execute? Finish time is the time of the each request. Okay. So finish time is not the time of the algorithm, it is the time of the each request. For example, this request is starting from here, finishing here. This request starting from here, finishing here. And we are drawing line for this. This is finishing here, this blue one. This is finishing here. And you are seeing gray lines drawn here in this picture according to the finish time. Now, what I'm saying, I answered your question or not? Or your question was a little bit different? Yeah, starting point. No, it's starting request, which is what you design in algorithm, the standard request, right? In the previous algorithm, it was, we were going according to the starting time. Yes. But here in this algorithm, we will go with the finish time. Okay. We will consider finish time and also compatibility, but we will mainly check finish time. In the previous algorithm, we were checking starting time. Let's see first and then everything will be clear. Okay. That is the only difference here. In the previous algorithm, we were going with the starting time. And here we are going with the finishing time. That is the only difference. So array A is same, start finish same, Q1 S1, Q2 S2, Qn is same. Output S would be some output with talks scheduled A. So all the algorithm is same except this line, except this step number one. Sort talks by finish time. So now First, what you have to do? You have to sort your task according to the finish time. First, second, third. So, or you can say Q1, Q2. So now you can see, for example, this is finishing first, this is first. And then this is Q1, this is Q1. And then this is Q2. This is Q3. This is Q4. This is Q5. Okay, and so on. And so on. Okay. So here we were sorting it according to the starting time. And here we are sorting, this is the first step, sorting it according to the finish time. Okay. And then step 2, S. S is initially 0. Again, that loop J is starting from 1 to N. And then we are checking Q1 is compatible with S. Okay, Q1 is the first, and there is no anything in the S, so that's why it is compatible. So Q1 is compatible with S. Yes, it is compatible because it is for coming for the first time. So Q1, according to finish, this is the Q1. It is compatible, yes. And there is no anything inside the S and with which we will match and say, no, it is not compatible, but it is compatible. Compatible, and then we are adding. Q1 is added in the S. Then we are going again. J is equal to 2. And for Q2, now this is Q2. And then we are checking Q2 is compatible with S. No, it is, the finish time is after this, but it is within the process of the previous one. It is it is starting before the ending of the Q1. Okay. So that's why it is not compatible and we are not adding it. And then we are going next and J is equal to 3. And then this is Q3. And then we are checking. Okay, finish time is after that. According to this, finish time is what? Finish time is greater than this one. Okay, that is no issue. But it is compatible because it is starting after that previous Q1, which is existing in S. It is starting after that. Yes, it is compatible, and then we are adding. So for compatibility, you are always checking two conditions, starting, finishing both. But this is just a starting, okay? And in this way, if we will go, we will get this orange highlighted answer. If you will execute this loop in this way, you will get this orange highlighted answer. And in this answer, you have how many tasks will be returned? Finally, S will be returned, and that S will have 6 tasks in it. And now, when you will have 6, from our previous knowledge, we know that according to this problem, 6 are higher. You can think some other solution if it is possible, 7 or something, but it is not, I think. So then this algorithm with the finish time is what? It is optimal or not? It is giving us an optimal answer. And if it is giving an optimal answer, then you can say, according to the definition of proving correctness, that this algorithm is correct. This algorithm is correct. Any question up to this point, Understood? So now assignment number 1, C. There is a greedy change making algorithm for making. So the algorithm is greedy change making algorithm. You will give some currency and it will change your currency into other, into coins or what. Change for making change. And the US coins that you have to consider is quarter means 25 cents, dime mean 10 cents, nickels mean 5 cents, pennies mean 1 cent. And you have to design some algorithm, or you don't have to design, but you have to show that this algorithm is correct or not, because that algorithm, greedy change making algorithm, is already existing. So the algorithm, that algorithm will do what? Whatever the value you will give, it will give you the fewest number of coins possible. It will give you change of that value, but that algorithm will try to give you fewest coins, minimum number of coins. Huh? The algorithm will do what? It will choose the largest coin always. For example, for this 25 cent, if you will give them 50 value, it will give you two coins of 25. Huh? Fewest, huh? Will give you two coins of 25. If you will give it 60, it will give you two coins of 55 and one coin of dime. Hmm? 10 cents. This is what it means. So the algorithm always choose the largest coin that is less than or equal to the remaining amount of change needed. If you will give 50, it will give you two quarters, which means 25, 25, 50. If you will give it 75, or sorry, 65, it will give you two quarters, which means 50 is gone. And what is the remaining amount? 15. And then it will try again the maximum, the biggest coin. 25 is not possible, then it will take this one dime. And then 5 is remaining. That is called remaining amount. So algorithm always choose the largest coin, which is less than or equal to the remaining amount of change needed. Huh? From 65, 50 is gone. Remaining amount is 15. Again, the largest coin. 25 is not possible. Next is what possible? What is possible then? This is the largest then. 10 dime, which is called dime. Then you will say one dime. And then 10 would be subtracted from that 50. And then 5 will remain. From that remaining amount, it will try this. No, no, this one nickel is possible. And then you will have zero balance. So until the amount is zero. Now the algorithm will execute like that. So now question is, you have to prove or disprove that this greedy algorithm, this is also a greedy algorithm. So you have to prove or disprove that this greedy algorithm always produces optimal answer, optimal solution for any change. For any change. This is theoretical question. You have to go by counter example, okay? Because here we talked about counter example. So you have to find the solution of this problem. You have to show that this algorithm is available on the internet. What that algorithm is doing, that it's working is depicted here. Huh? So you don't have to write the algorithm. Its working is already given there. You have to prove or disprove that this algorithm working is producing an optimal answer or not. You have to prove this through counterexample. You have to find some counterexample through which you can negate this theory. Or if you will not be able to negate this theory, then it will remain correct. Okay, now how we can prove that the algorithm is correct through mathematical induction? How many of you already know that what is mathematical induction? Raise your hands. How many of you already know that what is mathematical induction? Raise your hands. Nobody knows. Have you studied discrete mathematics? With me, I think. then, then how you can say that you have not studied discrete mathematics, huh? Now you know that you have studied this in discrete mathematics, huh? So now we have to prove the correctness of the algorithm through mathematical induction. But before that, as you were forgetting what is mathematical induction, so this is uh, for your memory, that you have to do these three steps. What is mathematical induction? Through this mathematical induction, we will prove again the correctness of the algorithm, and there are three steps that you have to do. What are those steps? Number one, you will consider the base case. You will consider what? Base case. You will assume some statement, and then you will show that this statement is true for the base case. When we are saying property holds, there is no need to. When we say property holds for a base case, it means true. There is no need to repeat this true here. Property holds. Whatever the problem will be given to you, whatever the initial state of that problem, you will put the initial value into that, and then you will show that the problem is producing correct result for that. That would be your base case. That would be your base case. And then second step. Here in this second step, you have to suppose something. You have to assume something. You have, by the way, for this, before starting it, you will assume that this is the theory. I'm using the word theory. That theory can be equation. That theory can be a series on the left-hand side and the right-hand side. That theory can be an algorithm. And you will assume that this theory. And then you will show, for the first step, then you will show that that theory is true for the initial value of that problem. That would be called base case. In step number 2, then you will assume that that theory is true for some arbitrary number. Arbitrary is like random. So then you will assume that that theory would be true for some arbitrary number k. You will put k into your theory, into your problem, and you will form some equation. And then in step number 3, in the previous step number 2, you will assume that this theory is true for k. Either it is true or not, but you will assume, because this is assumption. And then in step number 3, you will show by using that previous step 2, you will show that this next step will be which will become k plus 1. Previous step is k, and next step is k plus 1. Yeah. Previous step is k, and the next step, and this next step is what? K plus 1. Now you have to show that this step k plus 1, the theory is also true for the step k plus 1. In step 2, you will assume. But in step 3, you will have to show, you have to prove by using your mathematical knowledge. You have to prove that this theory is true for k plus 1. This is called mathematical induction. And you can use this mathematical induction, especially for recursive algorithm. But if you want to use it for loopy algorithms, you can use. Loopy algorithms are the algorithms in which you are using loops. For example, here, we are taking an example of a factorial algorithm. And what is factorial? For example, what is the factorial of 5? What is the factorial? It is equal to what? 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. It is equal to maybe 120. Okay. So this is called factorial. Either you can start from here, and then you can go up to this n, or you can start from n and then you can come back up to 1, not 0, because it is multiplying. 0 will multiply the whole thing 0. So now you have to make the theory of this factorial algorithm. Now theory is, consider an algorithm. So there is an algorithm which is computing what? Which is computing the factorial of some positive number n. Non-negative means positive. So there is an algorithm, you are giving some number n to it, and it is calculating factorial of it. And that factorial is represented by n factorial. And the definition for n factorial is what? This is the definition here. If you will give some starting value, starting number 0, and then the factorial of that 0 would be 1. Okay. And if you will give some number n, and then factorial of that n would be what? N multiplied by that n minus 1. 1, which means if n is 5, then 5 multiplied by 4. And you will take 4 factorial, and you will take the factorial of the 4 again. But 5 is separated. Huh? So which means uh, this 5, 4 factorial. And then you will call it again recursively 4 and 3 factorial. Okay. And then you will call this 3 factorial again, and then 3 multiplied by 2 factorial, and something like that. This is now the definition. For all n, and n is what? Greater than 0, which means positive. Positive number, not 0. So here in this mathematical illustration, starting value is also given. So the algorithm is what? Factorial. You have to calculate factorial. Definition is given for finding the factorial. And from this information, what you can find? The starting value, which is 0, is also given. If you will give n is equal to 0, the algorithm will give you what answer? What answer algorithm will give you? I'm asking you. I'm asking you, are you sleeping? So if this is an algorithm for finding the factorial, and if you will pass n is equal to 0, then according to this information, this algorithm will give you what answer? 1. Because factorial of 0 is 1. So the base case is also there. Huh? In this information, base is there. If we have to prove that some algorithm is correct or not by using mathematical induction, we have to perform these 3 steps. First is base case. Second is arbitrary case, but the title for this case is called inductive hypothesis. Second step is inductive hypothesis, IH. You can call it IH. This is base case. And final step, K plus 1. K plus 1 is called inductive step. Huh? This is inductive step, you can say. Now, an iterative algorithm for the factorial is given. Iterative means this algorithm is containing loops, not recursion. Huh? For recursion, it is easy, but for factorial, how we can use that? Okay, in this algorithm, we are passing some number n into it. Look over this algorithm. I'm giving just illustration speedily. We are passing some number n into it, and then we are checking if n is equal to 0, then we are returning 1, which means this thing. If number is 0, the factorial is 1. Else, if this number is not 0, if number is 5, then we will come into this else portion, and all these statements are under this else. And then here we are saying product some variable, and we are calling it 1. And then we have a loop for I from 1 to n. If n is 5, this loop will go from 1 to 5 if n is 5. Huh? If you passed n is equal to 5, 1 to 5, this loop will go from 1 to 1. Initially, the I has 1. And then here product is equal to product multiplied by I. Product is 1. So 1 multiplied by 1. And then your product will have 1. You will go again, I will become 2. So 1 multiplied by 2, it is going in that direction. 1 multiplied by 2, and the product will become 2. And then I will become 3, So product previously is 2, 2 multiplied by 3. So the product will become 6. And then it will become 4. So product previously is 6 and this is 4. And then you will have 24. And similarly for the last, you will have 120. This loop will be finished and this product will be returned. This is that algorithm. The question is this algorithm is correct? Now we have to show that this algorithm is correct by using mathematical induction. And we have this information available. Even this, if this information is not available, no issue. This is necessary to be provided. And we have to show that this algorithm is correct or not. Okay. Prove by induction. We know that in induction we have 3 steps. Mathematical induction, 3 steps. First is base case. So if the base case values are not given here, but we can take the values by ourselves. And then we can say, we can start from 0. According, if n is equal to 0, it will return 1. Huh? This is the base case. This if condition is representing base case. And this else is representing other values. So base case, and that you can say, if I will take n is equal to 0, the algorithm will return you what? If n is equal to 0, it is returning you what? 1. The algorithm returns 1. If you will give n is equal to 0, it is returning 1. And what is the definition of the factorial mathematical definition? In the mathematical definition, we know that for 0, it will give us 1. Huh? And when n is equal to 0, algorithm is returning 1. And by mathematical definition, for 0, it is giving us 1. Thus, we can say that the algorithm is correct for n is equal to 0. Step 1 is proved. Huh? Step 1, which is the base case, it is proved for the initial value. Now, what is the next step? I have to assume something for k. And then what is the next step? I have to prove the algorithm for k plus 1. Again, base case is what? For the initial value of that problem. Here the initial value is 0. So we have shown that it is true for the algorithm is correct for n is equal to 0. What is the second step? We have to assume that the problem is true for k. Assumption, we have to assume. And what is the third step? Then we have to show that the next step, which is k plus 1, is also true. Problem is also true for the k plus 1. We have to show step by step mathematically. But for step 2, we don't have to show. We only have to assume it is true for k. Let's see how you can do that. Now this step number 2, inductive hypothesis. And here we are assuming, okay? You can write the word assume or suppose or whatever. Huh? And here we are assuming that the algorithm, this algorithm. And here we are assuming that this algorithm will calculate the factorial for some arbitrary number k correctly. We are assuming. And here, if we will give n is equal to k, which is not 0, some other number greater than 0, and then the algorithm will come here, product is equal to 1, for I is equal to 1 to n. This loop will go from 1 to n. And then product is initially 1, so 1 multiplied by 1, you will have 1. And in the next, you will have 1, I is equal to 2, 1 multiplied by 2, you will have 2. And in the next, I is equal to 3, and then you will have 2 and 3 here, and you will have 6. So 1 multiplied by 2, multiplied by 3, multiplied by 4, multiplied by 5. And if you have n is equal to k, then it will go up to, multiplication will go up to k times. 1 multiplied by 2, multiplied by 3, multiplied by 4, multiplied by 5, and so on, multiplied by k. This is what I'm going to write here. Assume the algorithm correctly computes k factorial for some arbitrary positive integer k. This is our assumption. Huh? This is our assumption. It means when we will give this factorial and if n is equal to k, this algorithm will give us what? It will give us cofactorial. Huh? It will give us or not? Yes. So that is factorial k will give us what? K factorial. We are just assuming. Okay. We are just assuming. In other words, in open word, you can write 1 dot 2 dot multiply by 3 dot and so on k. Huh? This is what I want to say. Huh? This is equal to what? This is equal to k factorial. And this is what you are assuming here in this step 2. Huh? In this step 2. Now we are moving toward the next step, inductive step for the k plus 1. And here we have to show this, that the algorithm is correctly computing k plus 1 factorial. We have to show this step by step mathematically. And when we will be able to show that properly, then we can finally say that the algorithm is also true for the k plus 1, and we will give our final statement. So inductive step. Previous one was the inductive hypothesis. You are making a hypothesis. Huh? You are building a hypothesis. So that's why the assumption is assume is there. Hypothesis means mafruza. And inductive step. Now, what is that inductive step? Now we have to show that the algorithm will correctly compute the next number. What is that next number? K plus 1. And the algorithm will calculate k plus 1 factorial correctly. Now we have to show that. So if we will give n is equal to k plus 1 to the algorithm will go into the else block. Okay? It will go into the else block. Huh? The algorithm will, if n is equal to k plus 1, it will not execute this. It will go to the else block. And the loop will iterate from I is equal to 1 to k plus 1. If n is equal to k plus 1, then the loop will iterate from 1 to k plus 1 because your n is k plus 1. Okay. And the loop will iterate from I is equal to 1 to k plus 1. Understood up to this point? When the loop will complete, then the product variable, when the loop will complete, how many multiplications you have in that product, okay, then the product variable will hold this value, starting from 1 multiplied by 2, multiplied by and so on, multiplied by k and k plus 1. K plus 1 is the next step, huh? And we are showing also first k and then k plus 1. Correct or not? Mathematically correct or not? Yeah. Now this thing that you are seeing, 1, 2, and so on k, you already have calculated in previous step what is this, huh? And you already assumed that this is true. If you will give n is equal to k, it will give you k factorial. It will give you k factorial. You already assumed that algorithm will give you the result correctly. You already assumed in the previous step. That was your assumption, huh? And if that was your assumption, okay, in the next, I am saying I can write this in that way. I am separating this entity from that way. Mathematically, yeah, just separating. And I am giving it a label that this is equation 1. And then by using inductive hypothesis is previous step where you have assumed n is equal to k. And then I can say this is what? This is my k factorial in the previous step. By using, this is my inductive hypothesis. This is my inductive hypothesis. Okay. So then I can replace this entity in equation 1 by k factorial, as you can see here. K factorial multiplied by k plus 1. Okay. Clear up to this point? Okay. Now I have to show that this k factorial multiplied by k plus 1 is k plus 1 factorial. I have to make this. I have started my equation from here. I went up to this equation 1 and I said that here in this is the previous step, and I replaced that previous step here. But now I have to show that here I will get k plus 1 factorial. What is the definition of factorial? If you will see the definition here, n factorial is what? N multiplied by previous numbers and its factorial. For example, if n is equal to 5, then 5 multiplied by 4 factorial. This is what it means. And if you will look over here, k plus 1 multiplied by previous number factorial. Huh? Are you seeing that definition here? The definition of factorial is for 0 this is base case, this is that one. This is mathematical definition. Huh? Already proved. And here I am saying, okay, this is that next number, k plus 1. And then you are multiplying it with the previous number. And if your previous number is, for example, 4, then here what you are saying, 4 factorial multiplied by 5. So now after putting this thing 1, 2 and so on, k factorial, okay, k factorial k, which is what? Which is equal to k plus 1 factorial. This is what I want to say. This is equal to what? K plus 1 factorial. How? Mathematical definition, mathematical formula for factorial is this. If you have n factorial, that is equal to what? N multiplied by previous number, 1. Subtract 1 from it. Huh? And its factorial. So if n is 5, 5 multiplied by 4 factorial. This is what it means. And what it means here, if k is equal to 4, then it will become 4 factorial and multiplied by 5. So this representation, this mathematical representation is then equal to, if I can write that k factorial multiplied by k plus 1, this is equal to what? This is equal to k plus 1 factorial. I can write it like that or not? Huh? The definition for factorial is what? N factorial multiplied by n multiplied by n minus 1. You are understanding n minus 1 clearly, but not k. Huh? Are you understanding this? So this is what? Here your n is k plus 1, okay? Here in this representation, your n is what? K plus 1. So if I put k plus 1 here, n is equal to k plus 1 factorial. Huh? This will become k plus 1 factorial. And then it will become n is equal to k plus 1. And here k plus 1, when you will put k plus 1 minus 1, 1 gone. Huh? And then you will have only what? K and this factorial symbol. K factorial k plus 1. This is the same or not? And this is equal to what? K plus 1 factorial. And I am also saying the same thing, that this equation 1, which is happening in this situation at that point, now according to the definition, what is the definition? K plus 1 factorial. This is equal to k plus 1 factorial according to the definition of factorial. According to mathematical definition of the factorial, it is equal to what? K plus 1 factorial. And now this step number 2 is proved. And then I can say that the algorithm will return what? K plus 1 factorial for this inductive step. And then finally, what you can write by the principle of mathematical induction. The factorial algorithm correctly computes n factorial for all positive integers n. This is the theory. I can give you the answer, okay, prove by mathematical induction that the following algorithm can correctly compute n factorial for all positive integers n, and I will give you that algorithm also. How many of you have understood this last step? K factorial multiplied by k plus 1. Raise your hands. How many have you understood? Ghazi, Madri, huh? Madri, understood? Okay. Okay, this is now assignment number 1, part D. Prove the correctness of the following Fibonacci algorithm. Fibonacci algorithm is given here. You have to prove it through mathematical induction that this algorithm is correct. This is now will give you the idea that how the question will come and how the you have to answer like this, huh? Okay. Loop variant. The previous two methodologies were easy. Were easy means through those methodologies, you can prove that some algorithm is correct or not in defined steps. Okay. But here, this methodology that you are going to see or experience, it is totally different from the previous one. This is more analytical. The previous one were more close to mathematics, okay? But this one is more analytical, theoretical and analytical. So you have to think and then you have to present your argument by and then by using those arguments, then finally you have to say that your algorithm is correct or not. This is the last topic of your CLO, okay? So how we can prove that the algorithm is correct through loop invariant? But first, so we will use this methodology to prove that the algorithm is correct or not. And you can use this method only for those algorithm which involves a loop. That's why it is loop invariant, okay? If the algorithm doesn't have any loop, then you cannot use this method over it, okay? It relies on identifying a property. When algorithm is given to you and you have to use loop invariant, then initially again you have to form a theory. You have to build a statement first. And that statement will be called property. You have to identify a property. That property means you have to identify some statement in it, which you want to show that this is true for all the cases. And that property, we will call it loop invariant. Okay. You have to identify, I am giving you simple words that you have to identify statement. Huh? That statement would be called property. Okay. And you have to identify that property from the given problem. And then that property is basically called loop invariant, which you have to show that it is true for all these three steps. What are these three steps in the loop invariant? Initialization, maintenance, yes, and termination. So for the initialization, these are the definitions, okay? These are the definitions. You have to take it and understand it. And if you will understand these, then it would be easy for you to apply it on any example. Initialization. You have to show that your loop invariant, which is your statement, which is your property, which is your theory, you have to show that your loop invariant is true before the first iteration of the loop. So your loop is there, loop has not started yet. Before the first iteration of the loop, you have to show that your loop invariant is true. Before the start of the loop, okay? If I is equal to 0, I less than or equal to 5, I plus plus, if this is the loop, you have to show that your theory, your loop invariant is true before I is equal to 0, before execution of the loop, okay? So this is one step that you have to show. Keep it in your mind, the definition. Maintenance. If the loop invariant is true before an iteration of the loop, okay? If loop invariant is true before an iteration, it remains true after that iteration completes. If some loop invariant is true before the execution of the iteration, it will be true after the completion of the iteration. Okay. So it is something you will check I is equal to 0 before you checked as initialization. And then after I is equal to 0, if it is true, it is also for the next, it will be true. You will see. So you have to take this definition also in your mind. Termination. When the loop will terminate, when the loop will be finished. The loop invariant combined with the loop termination condition. When the loop is terminated, then the loop invariant combined with the loop termination condition. If you will check this loop invariant combined with the loop termination, which means when the loop is terminated, what is the situation there? And if the loop invariant is true, then you can say that your algorithm is correct. This is the termination of the loop. This is the in-between processing of the loop, okay? And this is the before the initialization of the loop. Now let's see. Example, linear search. So these are the definitions for these things. Initialization is what? Before the start of the initialization, you have to show that your theory is correct. Your loop invariant is true. Huh? Maintenance is what? In between the processing of each iteration of the loop, you have to show that your theory is correct. Loop invariant is true. If some loop invariant is true before the iteration, it remains true after the iteration. It is in between. Huh? Termination, when the loop terminates. So now if when that situation happens, that loop is terminated, now you have to show that your loop invariant combined with this terminated situation, you have to show that it is true. And if it is true, then you can say your algorithm is correct. And if it is false, algorithm false. Linear search. Example is linear search. Prove the correctness of this linear search using loop invariant. This algorithm is given. It is linear search. Linear search is what? Elements are given and you have to find the element in the array. Huh? In the array. And this A is the array, V is the element that you have to find. And here for I is equal to 0 to length of A. Length of A. If your array has 5 elements, then length of array will give you 5. 5 minus 1, 4. And this loop will execute from 0 to 4. This loop will execute from 0 to 4 if the size is 5. And then here you are checking. First I is equal to 0, so A into 0 equal to V. V is that element that you want to find. If it is equal, return that I, which is the location of that element. If all the loop is finished and there is no equality here, then the algorithm will come here and it will return -1, which means V is not found. Easy, huh? Now you have to show that this algorithm is correct. Understanding is easy. We are taking simple examples so that we can understand this method, how this is going. Loop invariant. Before considering these three different steps, initialization, maintenance, termination. These are the three names of the steps. Before starting these steps, you have to make a theory. You have to make a statement, which you will check on each step that this statement is true. That statement would be called a loop invariant. And now we are making, what is our loop invariant here? At the start of each iteration, I for this for loop, at the start of each iteration, I of the for loop, the element V is not present, is not existed in the subarray A0 to I minus 1. If your iteration is ith iteration, then we are assuming that loop is going for the ith iteration, then we are assuming that in the previous subarray A0 to I minus 1, element V was not there. So that's why we are going for the ith iteration. Okay. This is the meaning of this statement. So what it means, once again, at the start of each iteration I of the loop, element V was not existed in the subarray, in the previous subarray A0 to I minus 1. When you have not found the element at A0 to A minus 1, only then your loop is going for the next ith iteration. This is what it means. So now we have to show that this loop invariant is true for all these three steps. Okay, let's see that. Initialization. For this, initialization I is equal to 0. What is the subarray then? If your array is this, I'm taking only maybe 3 elements, okay? Okay. This is, some elements are also there. This is your array. And this is starting from 0, 1, 2, 3, and so on. And here you have some, just this is minus 1. This is the minus 1. But there is no array. Your array is starting from here. For initialization, when here your loop is starting, your I is equal to 0. When your first iteration of the loop, I is equal to what? 0. And what is the subarray? Subarray can be 0 to minus 1. Your index 0 to minus 1. This is your previous subarray. Even this is not existing. This is empty. Array is starting from here, but you have to make subarray. So your previous subarray is then from 0 to minus 1, which is mentioned here. When the loop is starting here with I is equal to 0. So I is equal to 0, my iteration is I is equal to 0. My subarray would be what? If you will do that, if I 0, 0 minus 1, 0 minus 1, you will have minus 1. This is your subarray. And that subarray is what? It is an empty set. Nothing is there. Nothing is there. Which means my element V is not present in that empty area. Is not present when we are starting the loop from 0. Is not present. So what it means? It means loop invariant is true or not? True or not? It is theoretical, I said. It is theoretical and analytical. The main thing is you have to build a loop invariant. And then you have to show that this loop invariant is true in all these three steps. The first step is initialization. First step is initialization. What is initialization? Loop invariant is true before the first iteration of the loop. This is the definition there. If you have that definition, you will not do any mistake. What do you have to show? You have to show that the loop invariant is true before the first iteration of the loop. And here, what is the first iteration of the loop? I is equal to 0. If I is equal to 0, I want to show that at I is equal to 0, the subarray, what is that subarray? 0 to I minus 1. Put the value of I is equal to 0 in here. When you will put 0, it will become 0 to minus 1. Huh? And 0 to minus 1 means there is no any memory allocated for it. This is empty. And if it is empty, V is not there. Huh? Your element is not there. Loop invariant is true before the first iteration of the loop. And here I have made my loop invariant is what? At the start of iteration, each iteration I, you can write each iteration I, or you can say at the start of iteration when I is equal to 0, element V is not present in subarray A into 0 minus 1. Or you can say for the initialization step, you can say for the first iteration of this loop, for the first iteration is I is equal to 0. I have to show that when I is equal to 0, V is not in the subarray. This is what I have to show or not in the initialization. So, and then I am saying, okay, when the first iteration of the loop, at that time I was 0 and the subarray was 0 minus 1, and this 0 minus 1 was an empty set. And if it is an empty set, my element V is not there. Huh? My element V cannot be there in the empty set. And if it is not, this is my loop invariant. It means loop invariant is true. Okay. Step 1 is clear or not? Moving towards step 2, maintenance. What is maintenance? If the loop invariant is true before an iteration, it remains true after the iteration. This is the definition of the maintenance. If loop invariant is true before the iteration, it remains after the iteration. So now you have to check each iteration. Huh? You have to check the iterations of the loop before the termination. Huh? Termination is the next step. Huh? Termination is the next step. So now assume that the loop invariant holds. This is like mathematical induction. Here in the maintenance, you can take assumption. And in the next, which is termination, there you have to prove. Okay. Now you can implement the idea of mathematical induction also for this loop invariant. Actually, loop invariant is using the concept of mathematical induction, because initialization is like a base case, maintenance is like a assumption, is mathematical induction, and the next termination is like k plus 1. So that's why here in maintenance you can write something like that. Assume, we are writing because it is like inductive step, huh, of your mathematical induction. And here we are assuming that our loop invariant is true, holds mean true, at the beginning of an iteration I. This means V is not present in 0 to I minus 1. This is our assumption. Assume that the loop invariant is true at the beginning of an iteration I. So iteration I is going to start. When iteration I is going to start, what is the subarray? 0 to I minus 1. What is the subarray? You are not giving any feelings or responses or hoo-ha from your mouth. Huh? When you are not giving me anything, I'm understanding you are not understanding what I'm saying. Okay, I will go up to the end and I will ask a question. Either you have understood or not. Huh? So anyhow, assume that, so we are taking an assumption. Whenever you will go for proving through in loop invariant, you have to do like mathematical induction, but theoretically, analytically. Initialization you have seen. In maintenance, you have to assume, and in the next, you have to prove. And in maintenance, now we are saying Assume that our loop invariant is what? Is true at the beginning of each iteration. And if that iteration is I, then what would be the subarray at this iteration I? Subarray is something step before. And then at that time, the array would be from 0 to I minus 1. And according to our loop invariant, we know that V is not present there. Okay. Yeah, V is not present there. So that's why we are going for the iteration I. Okay. We assume that the loop invariant holds at the beginning of an iteration I. This means V is not present in here. When it is not present here, now for iteration I, what will happen in this algorithm? Now for iteration I, what will happen? You will check it is equal to V. And if it is equal, you are returning the location. And if it is, and when all these things have will end, then it is not, it is returning that it is not found in the array, huh? When all this loop will end. So anyhow, in this algorithm, for this ith iteration, you are checking that either item is equal or not. Huh? There is only two possibilities. Either is equal or not. So now, after this assumption, here, when iteration I is going to execute, one thing is sure that in the subarray element V was not found. Then according to algorithm, when iteration I will execute, what will happen? We are checking that if AI equal to V, if the element is equal to V, then algorithm is returning the ith I, which is the location of the element, correctly indicating the position of V. Or if AI not equal to V, if if this condition is false, which means not equal to AI, then the loop will remain continue to the next iteration. Not or not. Here you can say for I is equal to 0. If it is equal, then it will return I. Otherwise, we will go back and I is equal to 1 and the loop will continue. Huh? Loop will continue. Okay, if AI not equal to V, the loop will continue to the next iteration, incrementing from this I to I plus 1. Yes. And now for I plus 1, we know that at subarray from 0 to I, it was not there. Huh? That's why we are going for the I plus 1. So now how you can write? How you can write theoretically? Since V was not in the A into, this is, we already checked that V was not in the A into 0 to I minus 1. It was not there. And we also checked here that in this second case, when loop continues to next, AI also not equal to V. It follows that V is not in A0 to I. If you are not understanding this, remove this sentence up to this and write this sentence directly after it. For example, when AI equal to V, we are returning I and we are saying that element is found. If it is not, then what it means? AI is not equal to V. It means now the algorithm will go for the next iteration. If it will go for the next iteration, what would be the next iteration? That would be I plus 1. Next iteration would be I plus 1. What it means? It means element was not found up to A. Element was not found in the array from 0 up to what? Up to what? Up to I. Up to I. MashaAllah. Why? What are you doing, all others? I'm asking simple questions and you all others are remaining silent. This is not hard. The things will start hard from from the next CLOs. This is simple steps. If the algorithm is going to the next iteration, which is I plus 1, what it means? It means previously up to ith iteration. From 0 to ith, we have not found element. And we have not. So it means it follows that V is not found from A to 0, 0 to I. You can write it like this by using these previous sentences, or remove that. And after that, you can write this sentence directly, because that concept is there. And then finally, you can say, okay, loop invariant holds for the next iteration, huh? Because we are assuming here the loop invariant holds at the beginning of an iteration I. This means V is not present in previous iteration, huh? This is our loop invariant hold at beginning of iteration I. What it means? V is not present up to the previous I. And here that situation is also, it is happening here. We are going to start I plus 1, which means V was not there up to from 0 to I. And this means loop invariant is true for this next iteration. Last step, termination. Loop will terminate in two situations. Case 1, when the element V will be found, and when the element V will not found. And now let's have a look at the termination condition. When the loop terminates, the loop invariant, you have to see the statement of the loop invariant, and then you have to combine with the loop termination condition. And then you have to conclude something that the algorithm is correct, huh? Case 1, V is found. Actually, this is last slide, okay? Actually, this is the last slide, huh? Case 1, time is going up, but just I need your help for 10 minutes maybe. Maybe earlier. So case 1, when V is found, you have to keep this algorithm in your mind, okay? Only then you will understand. So what is going on? Loop from 0 to length of A of I equal to 1, return I and return. So when it is equal, you are returning a location. When it is not equal, you are executing the loop. You are iterating the loop. When the loop will finish, when the loop will terminate, when the loop will terminate, when the loop will terminate, V is found. Case 1 is you have found the you found the element in between, and the loop will be terminated. Look here. If AI equal to V, whenever it will E, you are returning. Returning means you are going out of it. Loop is terminating. So this is one case when you will found the element in it. And other cases when you are not finding, and then you are going here and going again and again, and at some point the loop will finish, huh? And then you will come here and you are returning -1, which means V not found. So that step is also mentioned here, V not found. Two cases in the algorithm. Algorithm return I, and here I have written those sentences so that when you will go home and if you will read, you will understand what is written there. Algorithm returns I when I equal to V. Here you can see algorithm is returning I. When it is equal, it is returning I. So algorithm is returning I when AI equal to V. By the loop invariant at the start of iteration I. Again, now we are considering loop invariant, statement of loop invariant. At iteration I, if iteration is I, V was not found up to 0 to I minus 1 from our loop invariant, huh? This is my subarray. If the iteration is I, then from 0 to I minus 1, V is not there in the array. That's why we are going for the iteration I. Therefore, I is the first index where V is found. If this is the case that V is found, and if you are performing iteration I, what it means for the previous 0 to I minus 1, you have not found. Now you are going to perform this iteration I. And if the case is V found, then you will find it here. It is a possibility that you will find this element only at iteration I. From? We are saying I, so it can be first, third, fifth, whatever. But from the for the previous, from 0 to I minus 1, V is not there. The possibility of V is only available at the ith location. We are using ith location. Okay, this is the case of when V is found. So, okay, algorithm correctly returns its position. Because it is, then algorithm correctly returns its position. Now, when not found. Not found means what? Loop will complete all its iterations, according to the algorithm. Loop will complete all its iterations. Only then it will come here, which means V not found, So loop will complete all its iterations. And I will reach. And this loop is going from 0 to length of A minus 1. And when this loop will terminate, this I will go up to where? Up to length of A, not minus 1. Length of A minus 1 is the valid iteration. Length of A is what? The termination, the last one. Loop completes all iterations. And your I, which is the loop variable I, it will reach at length of A, not length of A minus 1, length of A one more time. For example, N and N plus 1, this is that thing. At this point, now the loop invariant states that V is not present. So again, loop completes all its iterations and I is reaching what? Length of A. You are coming where? You are, and the control is coming here. Return minus 1. Okay, now we are writing that thing. At this point, loop invariant state that V is not present up to 0 to length of A minus 1. Because here your I is equal to length of A when you have not found element. And then this is your last point. Then you can say from 0 to 1 point from that last point previously. From 0 to length A minus 1, we have not found element V. Okay, this is the whole size of the array. This means V is not there in the array size, entire array, or in the whole array. It is not there. And you can finally say that the algorithm will return minus 1. When this loop will complete all its iterations, when this loop will complete all its iteration, your iteration number would be equal to length of A. And then you can say from array from 0 to length of A minus 1, V was not there. And now the loop is terminated, and then you can say, and then you are returning it with minus 1, and then you can say element is not found. So you can say algorithm is correctly returning with the value minus 1. Okay, now after 3 steps, now you can say by showing the loop invariant And then you have shown that loop invariant is true for initialization, for maintenance, and for termination. And if it is true, then you can say that the linear search algorithm given is correct. Is what? Correct. Now assignment number 1, part E. I have uploaded the assignment, I think. So prove the correctness of the following binary search algorithm using loop invariant. Binary search algorithm is given here, and this loop is going on there. While loop. So using a loop invariant, you have to show that this is correct. Okay. And the deadline of the assignment is also given there for up to maybe 31. I don't know. I have given you 2 weeks maybe. And inshallah, in the next lecture, we will start with the lab exercises, okay? For this CLO.